Thank you, Nigel, for the introduction. So my talk will be about Oblivious Top-k Selection and applications to secure k-nearest neighbors classification. And this is also a joint work together with Kelong Cong, Jiayi Kang, and Jeongeun Park. Okay. So I will start by explaining the basics of oblivious algorithms and secure computation. So as you probably all know, by the end of today, FHE supports secure computation outsourcing. This means that a client can put some encrypted data on a server while the server is still able to perform useful operations on it. And example applications include machine learning as a service, such as in the previous talk. One challenge that we have in FHE is the program expansion that occurs when converting a plaintext program into a ciphertext program. So consider the following example program of the slide, which computes a branch. In a normal unencrypted world, you would first evaluate the top node, and then depending on the outcome, either go to the left or the right statement. In FHE, the first step is still the same, so we evaluate the branching condition. But then the second step is evaluated as an arithmetic expression between both y1 and y2. So as a result, both child nodes need to be visited, and this makes the procedure somewhat more expensive. Now, fortunately, this form of program expansion does not exist for so-called data-oblivious programs, where the sequence of operations and memory accesses are independent of the inputs. For example, suppose that we want to sort D elements, then we can use a standard sorting method, such as quicksort. This has time complexity order D log D, but unfortunately, quicksort is not data-oblivious, so we cannot implemented in FHE with the same complexity. Alternatively, we can use existing oblivious sorting methods, for example, with complexity order D log square D. So note here that the obliviousness comes at the cost of an extra log D factor. In contrast to normal programs, we can always visualize data-oblivious programs as networks. And for sorting, these networks consist of two main building blocks. We have the horizontal components, which are called the wires, and the vertical components, which are called the comparators. Then it works as follows. So a comparator takes as input two numbers on a wire and puts the minimum number on the top wire and the maximum number on the bottom wire. Then a sorting network for 4 elements can be built as on the right figure. So it can be done, in this case, using 5 comparators and a depth of 3, because there's 3 comparators in parallel. The sorting network from the previous slide is realization of what we call Batcher's odd-even sorting network, and this slide gives some more details on how it is constructed. Here the idea is a recursive procedure, where first the input is split in 2 halves, then each half is sorted separately. And finally, both sorted arrays are merged into one sorted array using a merge network. For the purpose of this presentation, I will not go into the details of how this merge is constructed, but internally also this is some recursive procedure. When we do the complexity analysis, one finds that Batcher's sorting algorithm has a complexity of order D log square D comparators and a depth of log squared of D. Note here that the relevant metric can depend on the implementation. For example, in single-threaded TFHE, you would mostly be interested in the algorithmic complexity, so the number of comparators. But when considering multi-threading, the depth is also important because it determines the minimum delay time. Now we move on to Oblivious Top-k Selection. The goal of a Top-k algorithm is to select the k smallest elements from a set of d given elements. And this situation occurs quite often in the client-server model. For example, you can imagine situations where a server contains a large database, but the client is only interested in a subset of it. Example applications include k-nearest neighbors algorithm, which will be treated as a case study later, but also recommender systems and genetic algorithms. Several other works have already considered Oblivious Top-k Selection in the context of secure computation, and multiple methods have been proposed. The first method is to use an oblivious sorting method, and then simply to discard the d-k irrelevant elements. For example, we can use Batcher's method, which was treated earlier, or we can use the so-called comparison matrix method, where each pair of elements is compared, but this comes at the cost of a quadratic complexity. Now, the graph at the bottom of the slide shows the number of comparators as a function of k, both for Batcher sort, indicated in dark blue, and for the matrix sort, indicated in light blue. So as you can see, for both blue curves, the number of comparators is constant as a function of k, which is because the sorting complexity is not parameterized in k. Alternatively, one can implement top-k by computing the minimum k times. This has a complexity of order k times d, and is indicated in the green curve on the slide. So here, obviously, the complexity is parameterized in k, and this results in a non-constant curve. Now, preferably, we would indeed like to have something which is parameterized in k, such as the green curve. But then, ideally, we want to stay under the complexity of Batcher sort, so under the dark blue curve. So what we desire is something like the red curve, and the next slides will explain how this can be achieved. To do this, we revisit another idea from Alex Sieve, who proposed a top-k method in the special case where your database contains 2k elements. Here the idea is that we will first split the input array into equal parts, both of size k. Then each part is sorted separately, for example, using Batcher's methods. And finally, we perform a pairwise comparison between the two sorted arrays. And then this works correctly because one can show that the final top-k result should contain exactly one element from each sorted array. This method can also be generalized to top-k out of d elements on the next slide. So this slide shows a generalization to an arbitrary number of d elements, for now just simply by copy-pasting the network from the previous slide 3 times. When we do the analysis of the complexity, we find that it is dominated by the first sorting phase, giving a complexity of order d log squared k, assuming we use Batcher's sorting network. Another interesting observation is that this pairwise comparison followed by sorting can be interpreted as an alternative variant of our merge procedure, but where only the first k output elements are of interest. This is what I will call a k-merge for the rest of the presentation. One way to improve this method from the previous slide is to replace the k-merge by a more efficient variant. Here our observation is that the Batcher sorting network, which we discussed earlier, contains an alternative merge procedure. But since we are only interested in the first k output elements, what we can do is truncate this method, this k-merge from Batcher, by removing the comparators that only affect the second half of the output. This gives us a complexity reduction from order k log squared k in Alex Sieve's merge to order k log k in our merge. So you can see an example on the slide. The left figure shows the network for Alex Sieve's tree merge, which contains 6 comparators. Then our tree merge on the right part of the slide contains 5 comparators. And note that this gap will grow for larger values of k. Then finally, this slide shows the network realization to compute the top K out of 16 elements. Here you can see the building blocks from the previous slides reappearing. For example, the boxes indicate K-merge procedures, and you can see the pairwise comparison at the very end. When we do the complexity analysis, we find that our method has the same asymptotic complexity as Alexiev's, but our solution contains fewer comparators in practice, which is mainly due to the improved K-merge. Also note that ours is monotonic as a function of K, which is mainly due to an improved version of the input partitioning, but I will not go further into this detail. Then we considered another possible method to compute top K, which was proposed by Yao. Here the idea is that we start with a pairwise comparison. Then the winners of this pairwise comparison immediately proceed to the final selection stage. However, for the losers, we can show that at most half of them will be in the final top K result. So these first pass through another selector before going to the final selection phase. Note that to implement this method as a network, we had to instantiate it with a suitable recursive base case and a symmetry condition. But for more details, I refer to the paper, which is online. When K is small, one can heuristically show that this method has a complexity of order D log K, so better than our method. But for large K, the complexity of this method becomes asymptotically larger than order D log squared K, so it becomes worse than our method. Now, since Yao's method works better for small k and our method works better for large k, we can obtain another improvement by combining both. So here the idea is that the combined network will recursively call either Yao's method or our method, depending on which one uses fewer comparators. Then the graph on the slide shows the final results. So you can see indeed for small values of k, our method, which is the green curve, will use more comparators than Yao's method, which is the blue curve. But then at some point will become more efficient than Yao's method. Then the combined method is always upper bounded by both methods, and in some cases even gives a modest improvement of up to 10% in number of comparators. Then as an application, we implemented secure k-nearest neighbors classification in the TFHE RS library. So k-nearest neighbors is a simple machine learning algorithm which has applications, for example, in image classification or network intrusion detection. And since there is not really a training phase, it is often used in applications where the training data gets updated frequently. It can be understood as a three-step method. So suppose we want to classify some new data point indicated by the question mark. Then first we will compute the distance between this new data point and all pre-classified database vectors shown in green stars and red triangles. Then in the second step, we will run the top k method to find the k closest vectors. And then finally, we will do a majority vote between these k closest vectors. So in this example, where k is equal to 3, we find that the green stars is the final category. In the secure version of KNN, all computation should be done homomorphically by the server. Note that in our model, we assume that only the target vector from the client is encrypted, and the database is owned by the server and given in clear text. So the first step is to compute the distance, but this can be done relatively cheaply in FHE. So for now, I will skip this step. The second step is running the top k network, which consists of comparators. Since comparison is a non-linear function, we use TFHE's programmable bootstrapping for it. And note here that In contrast to earlier slides, where each wire contains only one number, here we have 2 numbers per wire, so both a distance and a class label. So in order to deal with this, we just use two programmable bootstrappings per comparator. Then as a third step, the class assignment is done via majority vote, but since only k labels remain, this step is also relatively cheap. So we implemented this method in the TFHE RS library. And this slide shows some comparison to the most closely related work from ZS21. So this method assumes a very similar security model, and for comparison to other works, I refer to the paper. If you look in the second last column, then you will see that our absolute execution time ranges from 30 seconds, so half a minute, up to several minutes, depending on the size of your database. So we generated results for databases of 40 up to 1,000 records. If you want to go beyond that, then you will see that the execution time will quickly blow up. If you want to do a quick estimation, you can more or less extrapolate this linearly. So you see that it becomes rather infeasible for more than 1,000 records without hardware acceleration or multi-core. When we compare to the method from ZS21, we obtain a speedup of 1.7 times up to almost 50 times. And note that the speedup increases with larger values of D. Okay, so this talk described an Oblivious Top-k method with a complexity of order D log squared k in general, or order D log k for small values of k. Then this was shown by the implementation of a secure KNN classifier in the TFHE RS library, which can be up to 50 times faster than prior work for a database of 1,000 records. And since Top-k is an important submodule for various other applications as well, it would be interesting to see how our method can be integrated in different protocols. Okay, thank you.
In your comparison, so the previous implementation was using what library?
Also TFHE scheme, but I don't know which library.
Okay, so it's kind of so that your improvement you think is more. So how much of your so let me rephrase the question. How much of your improvement is due to the library, and how much of the improvement is due to your algorithms?
I think most is due to the algorithms because they use the method of quadratic complexity, so the pairwise comparison. Yeah.
Right. Oh, I'll go there.
Hi, thanks for the talk. You mentioned the step where you do the comparisons, and that's easier in FHE. But because you compare all the pairs, doesn't that take up a big chunk of the runtime?
Wait, can I go back? Yes. Do you remember which slide number? So the one about where we had the sorting, then followed by comparison, pairwise comparison. This one? So in this second step. Okay, line one. Okay, so the reason that so you do a comparison for each entry in the database. So in total, D distance computations. So this step, right? Yeah. Okay, so this is in total D computations, but the number of comparators is roughly D log squared k. So it's larger than the number of operations in the first step. And moreover, in the first step, doesn't use bootstrapping, so that also makes it much faster. Yeah.
Okay, one more question. So modern machine learning applications, the size of these k nearest neighbor is in the millions or billions of points. I know you showed results with 1,000. Do you see a way forward to get to 1 billion points?
Using this solution, probably not, because the execution time scales roughly linearly in D. There are other works who present, for example, interactive solutions. In that case, they can avoid the bootstrapping, which makes their solution faster. So with bootstrapping, I would say no. But if you want an interactive solution, there are other works about this. So in that case, maybe yes.
Oh. I'm just curious what you think is feasible here. Do you think d log k is possible? Are there known lower bounds in the different parameter regimes?
So there exist, for example, sorting methods which work in complexity d log d. So perhaps by adapting these sorting networks, you can somehow reach d log k also for large values of k. But the problem with these sorting networks, which work in order d log d, is that they are efficient in theory, so for large values of d, but then in practice, for normal values of d, they're less efficient than batcher sort. So maybe in theory, yes, but in practice, I'm not sure. Yeah.
What was the depth of the algorithm?
So the depth of the algorithm based on the adapted sorting is log d times log k.
Okay.
So yeah.
Okay. Would there be any significant overhead if your algorithm were to output the index of the elements rather than the elements themselves?
So if the output would be, you mean if the output would be the class labels?
Let's say you have a list and you just say it's the 20th element and the 24th, etc., rather than the actual elements. The output of the algorithm.
Yes. So now the output of our algorithm is the class labels of the first k elements, okay. And I'm sorry, I'm not sure if I really understand.
No, I think I understand. I was just asking if there was a difference between outputting the actual elements versus the index of them.
Okay.
There's no.
Yeah, there is some
difference.
overhead because in our case we need to use 2 bootstrappings, so it becomes basically twice as expensive.
Okay.
So there is indeed some overhead. Yes.
Thank you.
Okay, we will end it there. Thank you and thank all the speakers again.